Hello everyone. We are going to discuss an application of displacement method, metric displacement method for a 2D truss, right? So as you can see here, we have a truss with 6 members, right? Here a joint B, C, D, E, and F, G, right? So each joint you have a pin support, right? You know what is the statical indeterminacy and the kinematic indeterminacy. So statical indeterminacy means the number of members minus 2. So which means 1, 2, 3, 4, 5, 6. So statical indeterminacy is 4. The kinematic indeterminacy is the, so it simply means the unknown displacements or rotations at each joint, right? So since we are working in trusses, we don't have any bending moments, right? So any rotations, right? So simply we assume the loads are axial. So that means at each joint, you can only displace it in X direction or Y direction, right? So, but it is a pin support. So you can't move here or here. So that means degree of freedoms or is the unknown displacement. So the known displacement. So the degrees of freedom is 0 at each of these joint, right? So the kinematic indeterminacy is the summation of unknown displacements, right? But here you don't have any support, but only a joint. It can move it this way or this way. So that means you have A, you have 2, at B you have 0, and each time you have 0 unknown displacements. That because you know that displacement is 0, right? So kinematic indeterminacy becomes 2, right? In that case, for this kind of problem, since statical indeterminacy is larger than kinematic indeterminacy, you can use displacement method. If you use this, you have to reduce 4 redundant forces. If you're using force method, you have to remove 4 redundant forces. But here, you can solve for 2 unknown displacement at A joint, right? So they have given analyze the pin joint truss, stiffness matrix method. The area of cross section of all members is 1000 millimeters squared, and modulus of elasticity is 200 kilonewtons per millimeter squared. Find the displacement at A and the axial force in each member. So we should find the length, right? So we will consider the similarly as the last example in the beams. I would get this joint and the displacements. There are 2 displacements right now. In the first beam, there was only a rotation, right? Since that was axially rigid. So this is now you have displacement in this way, and you have to apply that displacement, and you have applied this displacement. So I will call this is my first direction, and I'm taking this as the positive direction. This is my second displacement direction, and this is the positive direction. Okay. So now the length AB. So length AC is directly 2.5, right? No problem. It is the length between these two levels. So here, if it is 2.5, this becomes 2.5 into, this is 30. This is 2. If this is L, this is L cos 30. If this is L, this is L sec 30. So that means 2.5 sec 30, which brings you how much? 2.88 or something, right? Let's call it 2.9. That's okay. So this is 2.5. So this is 2.5 into sec 45. So that brings you to how much? 3.53, right? So this is 2.5 into sec 60, right? 30, 45, this is 50, 15, right? So the angle is 60, 2.5 into sec 60. So that means 5. So this is equal to this length because these angles are equal, right? So if it is 5, this is 5 cos 30, right? So that brings you how much? It is 4.33 something. Is that right? 5 into cos 30. Yes, it's 4.33, right? So now my lengths are okay, right? So as you see before, now we need to, so there will be some actual displacement. So there will be a 60 kilonewton load here, and here will be 40. So there will be some displacements. So what we did was those unknown displacement, we set it to 0. So what you have to do is bring a fixed support to here, right? So what we are going to do is just here we fix it. So this is our primary structure, right? And then we should apply to this joint a unit displacement in the first direction. Similarly, what we did in the previous example, and a unit displacement in the second direction. Now it is unit linear displacement, okay? Okay. And once you apply, so once you add these three structures, you will get the final structure, right? So this is a bit complex. So I recommend you to watch the video we solved a P, right? So we take tension positive for the sign convention, and that those are the actions, right? In the each member, tension positive, and for the displacement, so we took this is positive and this is positive direction, right? And yes, now we need to consider the first one. I call this first, I call this second, and if you multiply it by the original displacement, and you should apply all this, and the corresponding outputs you should multiply it by displacement 2, and then when you add it, you will get the original structure without any trouble, right? The same thing, same concept, but bit complex due to several reasons. You will see why. And here, since you apply a fixed support to here, right? To apply, so I will draw one member. Let's say this is the ith member, right? Since you apply a fixed support, right? So you originally had 40 here, 60 here. But this fixed support has the exact same and opposite restriction force. This support restrict the force, right? This is the force applied by this joint due to the equilibrium, right? So that brings you your force at first direction is minus 40. It is in the other direction that we got the sign convention, and the second direction minus 60. These are the restraint forces, right? Okay. So no any temperature variation, no temperature movement in any of the member. So with this, we will leave that, right? And then this is the ith member. And since you don't have any member temperature variation or any elongation, all the members have zero force. This is the AR. It is 0, 0. There are 6 members, right? So now our first step is done, right? First step is done. We consider this and we got the displacements, right? Sorry, we got the forces. This is we are in displacement method. We calculate the forces and then the actions. It's done, right? So yes, it's here. The first step is done. And we move to the second. So we need to apply a unit displacement at A in this direction, right? So the total truss will be so each member. So I'm exaggerating this displacement. So this is very small displacement. Okay. So the finally it would be like this. So the every member get displaced, right? So I will take a common member. Let's call it ith member. It was originally like this, right? Okay. Now it's like this. So this is one unit displacement. So this has moved in this way. If you apply you this way, so you can see length is reduced. If the length is reduced, the applied force is what? A compression, right? So you can see original length is reduced. So that means the applied force on this member is a compression. Let's call it Fi. Okay. Let's call it Fi. Right? Fi. And this is theta I. For the ith member, theta I. Right? So that means this is 1 into cos theta I. Right? So the length reduction, the change in length for ith member is I. So you know F is A E L. So that brings you. So they have given A is same for each member, E is same. So the elongation is cos theta I over Li. So Li for the ith member. So L is changing. and this is the force applied. So this force is the compression in the member, right? If it is compression, this should be negative. Why? Our sign convention is tension positive. So still, so this try to, so this is at a joint, right? So you can take the components in this way and this way. So if these are same small deflections, you can check this is also theta I. You can assume because these are same 90. This is 90 minus theta. This is 90, then theta. This is theta I. So small rotations. I have exaggerated it, right? It's like a small arc, right? So in that case, this becomes Fi sine theta I. This is Fi cos theta I, right? So in the in F, you have a cos theta as well. This is very important, right? This is very important. So these are, so you apply a unit force, sorry, unit displacement. Okay. Sorry if I've told you unit force. This is not a unit force. This is a unit displacement because we are in the displacement method. And we check what will be the force applied at joint, right? So the joint force will be F cos theta I and F sin theta I, and it in the direction we took the sign convention. This is positive first direction and this is positive in the second direction, right? So that means S 1 1. So for the ith member, this is for the ith member, we took only one member. There are 5 members, 5 other members, right? Will be F I cos theta I and S 2 1 for the ith member. It is in the positive direction. This is the force per a unit displacement. That means the stiffness Fi sin theta I. Sin theta I, right? So to take this total F, total S11, you have to sum each of these, right? To each of these members, right? There are 6 members. So to take S21, right? So you have to sum up for these each member, right? So that brings you need a table, right? Similarly, you can, so this is the second step, right? So you can see now you find the stiffness coefficients for every member, right? Considering a representative ith member, and you find the force that is the action, unit action in each member. So in the action matrix, this is negative, right? Why? This force is in this one, this is positive. Why? It's in according to our sign convention. This is positive, this is positive, but this action is a compression for a member. So that means if this is here, it is negative, right? So we can determine the S11 is sigma. There are 6 members, right? So you have to sum these. This is sigma, right? So in the F, you have to write F as it is, AE cos theta over Li. I is multiplied by another cos theta, right? So that means cot squared theta Li. S21 is AE cos theta I into sin theta. Li, right? Here, can you see? So now first two stiffness coefficient are done. So now the action matrix. So this is AU, only the first. So only you can feel this part. This part will be in this third step. So this would be, so in each member, for ith member, it is a compression. So in each member, it is a compression. But don't worry, depending on this theta, it will be plus or negative. So that will eventually become tension or compression. This is your idealization, right? So just consider it is a compression for each member. So depending on theta, it will be compensated, right? So it would become minus F minus Fi, right? Minus Fi. So F is A E cos theta 1 over L1. So which brings you the final sixth member, A E cos theta 6 over L6, right? So this can be done by the second step. So we are applying a unit displacement in the other direction. Unit displacement. So we'll consider the member is like this then. So this is displaced. So the length is reduced. So that means this member is also in a compression, right? Member is in a compression. So you can divide the components, right? Fi sin theta I, for this is for the ith member. This is Fi cos theta I, right? So this length reduction equal to 1 into sin theta I. How? This is theta. So that brings you, this is theta. This is 1. So if you component in this way, this is 1 sin theta I. This is 1 sin theta I. So that brings you force is equal to A E elongation. Elongation is sin theta I over Li. right? This is just Young's modulus, right? So you can find, similarly, this is for the ith member, so that means Fs 1, 2. So the force in first direction due to the displacement in second direction. First direction is Fi cos theta. So that means this is into cos theta. So we have to sum up for 6 members. This is for the only for single member. So that means AE sine theta I into cos theta I Li S22 will be A. So it is Fi. So these two are in the original direction that we took the displacement. It's upward and to the right. But for the members, we consider tension positive. Okay. Keep in mind. So this is positive for the displacement sign configuration, and but the member force is compression. So that becomes a negative. Okay. So it is Fi sine theta. So that means this is sine squared theta I over Li. And for the actions, now I can go ahead, and this is Fi, right? Fi is AEI sine theta n, and it is a compression for each member. And don't worry, it will be compensated by the theta, whether it is compression or really for a tension. Minus AE sine theta 1 over L1. The sixth member minus AE sine theta 6 over L6. Right? Yes, we are done. So the third step is done. Right? Third step is done. And then we can add these 3 structures. So this was the original, we fixed it. We fixed it, right? And we apply a unit displacement in this way. And then we apply a unit displacement in this way. Okay. So this is still the displacement method, right? This is displacement method. So we calculate the joint forces. So that's okay, right? Then the member forces in each member, AR. That was 0, right? No any temperature effect or a second order effect in any member. So that was 0. Here, the force, sorry, here it is stiffness. Why? We are applying a unit displacement and the corresponding force is stiffness. Stiffness is okay. We found this and we found the actions as well. Right? We found the actions, but we need to multiply this by the original displacement. Let's call it D1, right? And we found the S and the action unit actions. We need to multiply these by D2. Once we add these together, this is the joint equilibrium. This is the forces in this joint. These are the forces in this joint. These are the forces exerted in this joint. What we actually did was we apply unit displacement at each time and multiply it back by the original displacement. So once you add it, this should be equal to the original force, sorry, or the equilibrium of the original structure at that joint, right? So we are going to consider that at original structure, right? Original structure, this is in equilibrium, right? This joint is in equilibrium. So the summation of, if you separate it, the summation of all the reactions will be zero, because this joint is actually in equilibrium, right? So that brings you the total horizontal force in this joint, total horizontal force. But there are external loads, but if you consider the total joint, the joint should be in equilibrium, right? So that brings you the total force in first direction is 0 and the second direction is 0, right? And here you went to find F, right? What was F? So the original member, it is 0 and 0. So this is the original force. So this is the F matrix. So you took it as minus 40 and so this is the restraint forces, you remember? And then you apply each force and calculate the unit displacement and calculate each force. That means the stiffness. And that is the S11 into the real displacement. And here it is S2, this is the second direction, S12 into D2. Here it is S21 to D1 along this second direction D1, because you apply D1 and in the first direction you apply a unit displacement and multiply everything by the actual deflection, right? In the second direction as well, you take the displacement. What is that? The force. These are the forces, unit forces, right? Forces per unit displacement. So S22 by D2. So you can solve this S11 and S12 and S21, S22. It's the same displacement method, right? D1 and D2, right? You can find this is already found. You can find this and you have to solve for this, right? So you need to consider what is the stiffness, okay? So for that, I will be considering a table, right? So actions as well, you can take from this, the same matrix. You remember action is equal to action in the R. So this was 0, right? No temperature effect or any other effect. and the unit actions into the displacement matrix. You solve this and you plug into this and find this one, the member forces, right? This is the displacement at that joint A. So I need to find these stiffness values. For that, I'll consider a table. So this is member. So this is theta. This is cos theta. This is sin theta. Sorry, I need cos theta, sin theta, and sin theta, cos theta. Sin theta into cos theta. So the member 1, 2, 3, 4, 5, 6. For member 1, theta is measured in clockwise direction from the horizontal level, right? Horizontal x-axis. So it is theta 60. For the second member, it's 90. Third member, it's 135. Fourth member, it is 150. Fifth member, it is 180. Sixth member, 210. So the cos squared theta becomes 0.25 and sin squared theta becomes 0.75 and sin theta cos theta is 0.43, right? Here it is 0, 1 and 0. Here it is 0.5, 0.5 and here it is 0.5 minus. Here it is 0.75, it is 0.25, here it is 0.23, 43. Here it is 1, 0, 0. Here it is 0. Here it is 0.75. Here it is 0.25. And here it is 0.43. Right? Okay. So then you do remember that in the each step you need to take this AE out. If AE was out, sin theta cos theta over Li, sin squared theta over Li. Right here, F in the F you have cos theta. That means cos squared theta over Li. If you take AE out, cos squared cos theta sin theta over Li. If you take AE out, so that's how to you have to find. So you know the Li values, right? So you can develop another table that is cos squared theta over Li, cos squared theta I over Li, sin squared theta over Li, sin theta cos theta in theta I over Li. That means you have to divide this. This is L. This is cos theta squared 1. You have to divide by L1. You have to divide by L1. You have to divide by L1. For this, you have to divide by L2. This you have to divide by L2. This you have to divide by L2. Right? And take the summation, because S11 is when you take EA out, it brings you cos squared theta I over Li. So that means EA cos squared theta 1, let's say this is theta 1 over L1 plus dot, the final one is cos squared theta 6, there are 6 members over L6. For S21 and S12, this becomes sine into sine theta 1 cos theta 1 over L1 plus dot, the last one cos theta 6 sine theta 6 over L6. And this is similarly, you can take EA out. It is sine theta 1 over L1 plus sine theta 6 over L6. So from that you can determine, and you add it up all, and you know the value of E and A. It is 1000 and 200. So sorry, 200 and 1000. So you can determine the stiffness matrix. So your stiffness matrix will become closer to this, right? No need to be exactly these values. One, 542, 1542, 180, 3, 7. So you can take the inverse of this using a calculator, right? So then you have this, right? So 0 is equals to 0 and 0 is equals to minus 40 and minus 60. So once again, I'm repeating, at the force method, so displacement method, we are checking the equilibrium of that joint, right? S into D. So we move this to this direction. This is 40 and 60 multiplied by the S inverse equal to D. So if you multiply it correctly, you should be obtaining D as 0.0003 and 0.0003, right? Both positive. So that means at A joint, our first coordinate is in this direction, so that has moved 0.003. So this second, along second direction, it has moved 0.003, right? So once you find displacements, right, so you can determine the forces, right? Because in the action matrix is the action matrix, so you know AE, so you have to determine now cos theta I, cos theta 1 over L1. So that you can determine. So these forces you can determine. There is no cos squared theta, sin squared theta, or sin theta, cos theta terms. Just the force, and that's a compression, right? A is 1000, E is 200, cos theta 1 you know over L1. The second one, AE cos theta 2 over L2. Third one is like that. Sixth one, AE minus AE cos theta 6 over L6. Those are the member action unit matrix, right? So once you plug that, you will ended up with action unit matrix as this. So it can be slightly different from yours, minus 64. Here it is. Four zero one six seven. 34614 minus 20045 and 46242 minus 73. 34678 19935, right? If you multiply, so you need to find this action. This is completely zero. You remember action R, because there was no any effect on the members once you fix the A joint. So this is AU. This is absolutely zero into D. TU found as 0.0033. And what is actually happening here? So you get the equilibrium using forces and multiply it by origin displacement, and you then find the displacement, and then you multiply the action units in that from that displacement and calculate the actions back on the original figure. This is zero. So once you add these, you get the correct final member forces. Our actions was the member forces, right? So when you plug this, your actions will be minus 29, minus 26.5, minus 2.9, 2.4, 12, and 15.6. So in the first member, you have minus. So that means this is in compression, right? These are positive. So that means those are tension. So this is pretty cool, right? So even you can do finite element modeling and check these results. They should be exactly equal because the softwares using this displacement method to find these, right? And finally, your structure would go 0.0003 in this way and 0.0003 in this way. And these are in compression, these are in tension, right? So you actually can see that it try to move this joint in this way, right? So that brings you, this should be compressed due to this load, this should be compressed, but that effect will be reversed for these one. These are pulled, right? So these should have tension. It doesn't matter. Anyone can solve this and actually get these forces. So this is it. Thank you.